Hello. In this video, we'll be talking about section 2.2, Systems of Linear Equations in 3 Variables. This will be continuing from where we had left off in section 2.1, which was talking about systems of linear equations with just 2 variables, x and y. Here we're going to be seeing 3x3 systems that include variables x, y, and also z. In terms of the solution scenarios we will either get systems that have a single solution, which are those that result in a solution set consisting of an ordered triple x, y, and z. Graphically, the ordered triple then would define a point that is the intersection of the 3 planes in space. You can see that with this example here. We have 3 different planes. Think about this as 3 infinite sheets of paper that all intersect at one point right there in the center. This would be the single solution where all 3 of these planes intersect, and therefore all 3 of these are going to be true. Instead, you could also get a system where you have an infinite number of solutions, which are those that result in an expression that is always true, such as 0 equals 0, 5 equals 5, some constant number equal to the same constant number. Graphically, an infinite number of solutions represents a line that serves as the intersection of 3 planes in space. You can see that with the example down here. We again have these 3 infinite-sized sheets of paper that all intersect along this single line. You will see this black line represented in this diagram here. This black line represents the infinite line where all 3 sheets of paper, or all 3 of these planes, intersect, and therefore those are all of the solutions. If you do not have a case where you have a single solution or an infinite number of solutions, you could also run into scenarios where you have no solution. These are cases where it results in a statement that is a contradiction, such as instead of a constant equal to the same constant, like 0 over 0 we talked about earlier, what if we had a constant equal to a different constant, like 3 equals 0? That would be a problem, as that is nonsensical. Graphically, a system with no solution is represented by 3 planes that have no common point in which they all intersect. For example, let's look at a couple of cases here. We have 3 planes here which do intersect for some of the planes. For example, the orange and greenish planes intersect along this infinite line, but the blue plane does not intersect on that same line. Therefore, it is not a consistent solution that is true for all cases. Same is also true for the second scenario here, where we do have 3 planes. Again, they do intersect in some cases. The orange and green planes do intersect along this infinite line. The orange and blue planes intersect along this infinite line, but they do not all intersect at any same place. Or lastly, and probably the most commonly thought of, if you have 3 parallel planes, which means that they do not intersect in any scenarios, like you have 3 pieces of paper all floating above each other, that means you're not going to have any consistent solution either. If you do have a solution in 3 variables, such as for the equation 2x plus 3y minus z equals 4, we call that an ordered triple, and we write that as x, y, and z. For example, the ordered triple 0, 1, and negative 1 is a solution because we should be able to plug that into the given equation and get a true statement. We can show that here. If I take that equation, 2x plus 3y minus z equals 4, and I plug in 0, 1, and negative 1 for x, y, and z respectively, that will give me 2 times 0 plus 3 times 1 minus negative 1 equals 4. 2 times 0 is 0, 3 times 1 is 3, and minus a negative 1 would be plus 1. Here I see that I get 0 plus 3 plus 1, and that is indeed 4, and that equals the right side of 4. Because we do get a true statement for this equation, that means the ordered triple there is a true solution here. Let's now talk about one of the most common methods used to solve a system of equations in 3 variables, which will be called the elimination method. First, what we're going to do is write all equations in standard form ax plus by plus cz equals d. This means if we have anything in a different order there, for example, if we have this z term listed first, we're going to rearrange that. Or, more commonly, if you have x, y, or z alongside the constant on the other side of the equation, then manipulate that as necessary. Then clear any decimals or fractions. This means if you have one of those coefficients on x, y, or z equal to, say, 1/2, then let's try multiplying the entire equation by 2 to make this nice and simple with just whole numbers. Then what you're going to try to do is eliminate one variable using two of the original equations. For example, eliminating z from the equations 1 and 2. Then you are going to eliminate the same variable from a different set of two equations, such as, again, eliminating z from equations 2 and 3. Then, as you may guess, we are then going to eliminate again, but in this case we're going to be taking those new equations, which we'll call 4 and 5, and eliminate a second variable, such as y or x. Then we'll substitute that first solution, whichever one we end up finding, into that equation of 4 or 5 to find a second solution. Let's say, for example, I solved for x, then I'll plug that into either equations 4 or 5 to solve for y. Then we will substitute both solutions for x and y into one of the original equations to solve for the other missing variable. In the scenario I've been talking about, that would be z. Then we would have our solutions for x, y, and z, which we can then state as an ordered triple. So parentheses, x, y, z. Let's demonstrate this with a guided example here. In this scenario, we have a system of equations provided to us. Notice a couple things, that all the coefficients are nice whole numbers, so there's no decimals or fractions to clear out. And everything is in the consistent order of ax plus by plus cz equals the constant d. Also, each of the original three equations are numbered. So our first equation there is numbered as equation 1, then we have equation 2, then we have equation 3. This is going to help us keep track of what we're doing. From here, we're going to try to eliminate one of the variables. And really, you can do whichever variable you want. It tends to be whichever tends to be the easiest one to do. If we look at our three equations, we notice all three of them do have 4z, although one of them is a minus 4z, I suppose. But that still means there's not much we would really need to do to eliminate that variable of z, outside of just adding or subtracting those two equations from each other. Say, for example, if I take equations 1 and 2, if we were to take equations 1 and 2 and add them together, the terms with z, this plus 4z and minus 4z, will cancel out, and what you'll get is just the sum of the x and y terms as well as the constant on the right side of the equation. 2x minus x will give us a total of 1x, or just x. Y and 3y will give us a total of plus 4y. And on the constant side, we have 3, 6, which will make a total of 9. Since we decided to eliminate z with two of those equations, we're going to take another pair of equations and eliminate the same variable. So we're going to try to eliminate z again. Again, thankfully, this was a pretty convenient example. Here we're going to take equations 2 and 3. And again, we're going to try to eliminate z, which we can simply do by adding these two. If we do so, the x terms combine, minus x plus 3x creates 2x. The y terms combine, 3y minus 5y gives you minus 2y. And lastly, the constant terms again combine, 6 and 2 make a total of 8. With these two new equations, which we will label as equations 4 and 5, we can then combine those two in a way to eliminate one of the other remaining variables, either x or y. Again, it is up to you in terms of whichever you'd like to do. In this case, the guided example decided to eliminate y. You may notice, however, unlike the original scenario, it's not as convenient where we can just combine them together and then the y terms eliminate. We do need to multiply one of those equations by some other whole number to try to get this to combine nicely. In the equation for 4, we have a plus 4y. In the equation for 5, we have a minus 2y. So if we were to double or multiply that fifth equation by 2, we would end up with something that would allow us to eliminate and cancel the y terms there. If we multiply that second equation by 2, which is shown there, we're going to instead get 4x minus 4y equals 16. This way, the 4y and the minus 4y can add together, combine, and cancel out. If we do that with those two new equations, though, we will also have to combine the other terms. The x terms, x plus 4x, will create 5x. Then the constant terms, 9 and 16, makes 25. From there, with 5x equal to 25, it doesn't take anything more than dividing by 5 to get x by itself. And if you do so, you will get your first solution here, which is x equals 5. With that first solution, we can then plug that into either equations 4 or 5. Notice we'll just use either 4 as it was or 5 as it was, so we're not going to use the altered version of 5, for example. In this case, though, they again chose to just look at equation 4, and they substituted x equals 5 in place of x right here. To do that, then we would solve for y by subtracting 5 on both sides. That gives us 4y equal to 4. And dividing by 4 will give us y by itself. Our second solution, y equals 1. Then with the solutions of both x and y, we can plug those into any of the three original equations. So the three that we have up here, because those all still involve z. If we know what x and y are, however, we should then be able to solve for z. As usual, it is up to you in terms of whichever you choose to do. The guided example here elected to do equation 1. So they substituted x equals 5 and y equals 1 into that first equation. Putting 5 in for x, you get 2 times 5. Putting 1 for y, you get plus 1. And then plus z will equal 3. We will first combine those like terms, the constant terms on the left side. 2 times 5 is 10, plus another 1 will give us a total of 11. And then to solve for z, we will subtract 11 to the right side. That gives us negative 8 equal to 4z. And then lastly, you can get z by itself by dividing by 4 and getting z equal to negative 2. Those would be our solutions for x, y, and z, which means we can write the final solution as a single ordered pair, shown here at the bottom, parentheses 5, 1, negative 2. Do be sure when you're writing your ordered pair that you do write it in that order, x, then y, and then z. That is it for today. Hopefully that helps you understand a little bit here about solving a system of equations with 3 variables.